Let's study two-dimensional closed topological quantum field theory in a fast, intuitive, as well as very sloppy manner. First thing we need are cobordisms. This is simpler than what it sounds like. These are two-dimensional orientable manifolds that interpolate between one-dimensional orientable closed manifolds. So what are the one-dimensional orientable closed manifolds? Well, a circle is closed and orientable, but so are multiple circles. And that's it. So we'll draw these pictures where we imagine that time runs from left to right. And we'll have something that interpolates between two of these guys. So we have a bunch of circles on the left and a bunch of circles on the right. Now we have a manifold that interpolates between these two. All those manifolds will look like this, where these two-dimensional manifolds can have holes in them. The number of holes we will call the genus. The number of circles on the left can be m, and the number of circles on the right can be n. Total number of circles is n plus n. These are basically all these manifolds. So these cobordisms form a category. And the category has a skeleton from which we can build all of these manifolds. Skeleton consists of 5 drawings. We go from nothing on the left to 1 circle on the right, or vice versa. Or we go from 2 circles on the left to 1 circle on the right, or vice versa. Or we just propagate 1 circle. This is the skeleton. So this is all we need to build all manifolds. For instance, to build a hole, we just glue the 4th one to the 3rd one. And if we do such a gluing, then we find a manifold with a hole. And so on. The second thing we need is the category of vector spaces. Over some field K. And we'll equip it with tensor product and other features. Now comes the crucial definition. A topological quantum field theory is a functor between the category of cobordisms and the category of vector spaces that respects all the necessary properties. So what does this functor do? So first of all, we have the first skeleton So it takes the empty space, which will associate to the vector space K. It takes it to the circle, which we will associate to the simplest vector space, which we will call A. Or rather, let's call it C. Then we also have the two circles are associated to the tensor product of two of these spaces. So this drawing goes from the tensor product of two C's to C. In other words, this defines for us a product. We have no order in the way we write our circles on left or on right. Which has as a consequence that this product will be symmetric. When we compose the second drawing, the third drawing. So we have a symmetric product. Moreover, we have this drawing, which maps C into K. So this is kind of like a trace or a linear form because we asked that all these operations are linear. And I've used that like this joint union of circles corresponds to tensor product. Of course, this propagation is just a unit map. If you wish, this codes that the Hamiltonian of the topological quantum field theory is 0, such that propagation is trivial. So this is the identity map in C. All right, that's a third part. Now, fourthly, some observations. We note that because this drawing, which goes from a circle with one orientation to a circle with the other orientation, this is like a bilinear form. And if we compose it with this other drawing, we get kind of like a snake, like this. And that looks topologically equivalent to the identity map. And because it does, this bilinear form must be non-degenerate. And from the previous reasoning that we cannot order circles, it is also symmetric. So then fifthly, we come to the conclusion, which is that a topological quantum field theory for closed one-dimensional manifolds, or interpolating between closed one-dimensional manifold, is equivalent to a commutative Frobenius algebra. Why is that? Well, a Frobenius algebra, C, is by definition a vector space with a product, which is associative, which one can see from composing pictures above. Moreover, it has a linear form, which we do, which can be thought of as a bilinear form, which is symmetric. to explain this, we can draw also this drawing once more of the bilinear form. Note that it is equivalent to first taking a product and then capping it off, such that the linear form gives rise via the product to the bilinear form. In other words, AB, where AB are element of C, is equal to the linear form, let's call it T, evaluated on the product. That's what we see from this drawing. All of the properties that we listed indeed make C into a commutative Frobenius algebra, which is what we wanted to prove. Lastly, there's an extension of this to an open two-dimensional topological quantum field theory, which I will not discuss here immediately.